Okay, so this problem asks us to determine whether a given tree is a binary search tree or not. So we are given this method right here, and we gotta do is essentially validate all the nodes and make sure that these three properties are adhered throughout. So the first one is that the left subtree of a node contains only nodes with key less than the node's key. So the node's key would be, for this tree, would be 2 right here, and the left subtree would be 1 over here. So is 1 less than the node's key? 1 is less than 2. So yes, that should be a true statement. And now we look at the right subtree of a node that contains only nodes with keys greater than the node's key right here. I do want to make note of one keyword here that isn't bold, but it is nodes with an S. So all the nodes on the right and on the left needs to apply these properties as stated. Right, so going back to here, 4. So it's 3. So is 3 greater than 2? Right, okay. Greater than the node's key. 3 is greater than 2. So yes, this statement is true again. And the next thing is make sure that both the left and right subtrees must also be binary search trees. So this means that, again, these properties don't just apply, let's say, to the root of the tree. You also need to apply to the rest of the tree. So over here, the same thing apply if there is more nodes here, and you get the point. So here is an example where of, basically all of the rules being adhered to, hence the output is true. Over here, you can see that we can go through the nodes by itself. So the left subtree, is it less than the node's key? 1 is less than 5, yes. And now we go over here, 4. Is 4 greater than 5? The answer is no, and for that reason we should return false. So it will only return true if all of the properties are adhered throughout the tree. Okay, so again, I think the tricky part about this problem is to really clarify and understand that they're asking for all the nodes, right, on the left, and all the nodes on the right. Perhaps an extra emphasis on the third requirements here. So yeah, I mean, I just explained what someone might do if they did not understand the problem clearly or entirely from the get-go. So what you might do is just check, keep on recursing and checking. Okay, make sure that it's like this node is less than this node is greater than this, but then we go here, this one is less than this one is greater than this. But then what we don't remember is that we also need to keep track of the upper and lower bounds, right? So if we take 5 for example, right, over here, and we go over here, and let's say we go down again, right? Let's say we have like a 0. Okay, that would still be true, right? But let's say we have something over here. Let's say we have a 7. Now is 7, less than the node's key? It is less than this one, but it isn't less than the root over here. So we could verify this by using the test case that this is indeed the expectation. So here, let's just use the case 2. Okay, So let's say we do have 0. This one here should still return true because, you know, it adheres to all the rules. So let's go ahead and see that in action. Oh, but this one is already false. So we have to fix this one first. Let's do 4, let's do 6, 3, let's do 4, and 7. Okay. Actually, we don't need 0. I think this would showcase the example. So again, 1 is less than 5, that is great. Okay, 6 is greater than 5, that is great. 7 is greater than 6, that is great. It's also greater than 5, which is great. And is 4 less than 6? Yep, that is great. But is 4 greater than 5? The answer is no. And for that reason, this one will actually output false instead of outputting true, as in it is actually a binary search tree. So let's check that out. Right, so it's false. So in order to make this one be true, maybe you guys can pause the video and think of like a number, right, just to make it true, or how we can go about fixing this tree right here. Okay, well, I think to make this true, something we could do is definitely have a number that is greater than 5. So a number that was greater than 5 is, the next number is 6, right? But however, this would basically like collide with this because we need a number that is actually like less than 6. This will also return false. So let's might as well go for this example. So yes, we're still returning false. So let's get back here. We've got to edit some more numbers so that yeah, the example can output something true. So maybe you guys can pause the video and just come up with a modification by yourself. Okay, all right, now I'll go ahead and do a modification. I'll put let's put a 7 here. I'm gonna make it this one an 8. Instead of a 5, let's make it actually it might be more easy to start with something from the top, right? And then this one is greater than, so let's put 9, right? 9, and then we can put a number that is greater than this. Put right here, put like 11. A number that is still greater than this, we can put a 6. It actually works right now. Okay, so this one should actually return true. Right? Again, expect true, but we return false here. Okay, so let's go ahead and write up our solution. Because we need to keep track of the upper and lower bound, so let's create a helper method. Taking the extra arguments of lower bound, and then an extra argument of the upper bound. Okay. Turn a boolean. All right. So first thing we want to check is for the base case. If there isn't a root node, it means that we could return true. So that's just a base case for us. So for the, I might as well just explain it in further, just in case somebody just want to figure out a bit more of the detail of when this case would occur and we don't have a root, and we return true. So of course the first case is, let's say the problem gives us an input of an empty tree. That is one case. We count that as a valid binary search tree. Another case is basically once we get to the end of the leaves, once we get to the end of the leaves, and basically it's like we haven't found something that is wrong, right? So yeah, we return true. But I mean, any times that we do find something wrong as in not everything adheres to these rules, we return false. Okay. All right. So now that we have that out of the way, let's actually make sure that the value is good to go. Okay. Value. Make sure that, let's see, the left. Okay. The root left. That's that value. We're just writing out the tech requirements in code. That's what we're doing, writing out the specs, Yeah, so nothing too crazy here. Otherwise, return false. And now we're gonna make sure that the right value, right? No, the value is less than. Oh, my bad. All right. Val is the case. And we also need to make sure that the left node is a valid binary search tree. Left, right, and both of these properties, these variables, should be true. Now we need to put something in here, right? These two arguments. So let's think about what to actually put in here to make this a correct solution. Okay, so we just call this the helper method. And what do you guys think we should put in the lower bound? So when we start out here, right, we have the node's keys value of 2. What would be the lower bound of it? Okay, so what we can put here is actually just like the minimum after the lower bound, and on the right we can put select the maximum. This would be like the upper bound. Yeah. So again, actually what we care about is not the immediate value, even though we do care about it. We also care about whether, like all of the values as we traverse down the tree adheres to the rule, right? And yeah, for that reason, we have to make sure that the rules apply, basically. So let me just read this one more time. Less optional. We know contains only keys less than the node's key. Alright, so make sure God value it is less than the upper bound, and value also is greater than the lower bound, else we return false. Okay, so when we move over here, the lower bound now becomes let's think about this. When we move over here, now when we check more, what happens is that we have to check that the value here, right, is actually the new lower bound. Upper bound. And when we go over here, our lower bound remains the same. Right. But our upper bound is going to be the value. So let's give this a try. Okay, let's go for the example. So we go 2 over here. Now the value here becomes 2. And you check if 2 is less than the upper bound. Upper bound is max, so yep, true. And then the lower bound is minimum, so it is greater than the minimum, so return true. So let's just make sure that this is the case first. Alright, and true. Okay, that's good. And now we check if is the left node tree valid. Valid. So we go to the left over here, and now we see that because we go to the left, now we put the lower bound as 1. Okay, lower bound is 1, and the upper bound is still max. Okay, so this would actually just return whether both is true. So, see here is true. Okay, so I think something is wrong here. So there's a problem there. About greater than, okay. Okay. 2 and 1 here is 1 is to the upper bound. Actually, when we go here, it's not like we care to update the upper bound, right? We just want to make sure that it is less than. So actually, we should put the lower bound here, and then make it the value here. Because like if you think about it, once we move right here, right, we just want to make sure that that everything on the right is less than this, and everything on the left is, you know, yeah. Alright, I think this should work. Okay, seems to work. And yeah, so definitely a problem that isn't super duper obvious. And if you go through, if you hit a mistake, I think this is quite normal when practicing. But again, which is why you need to like practice and just like get used to, you know, just thinking for these problems. And yeah, so yeah. So again, right, for this one, so we just go to the example again. Go to the left, Right now it's 1. Now 1. The lower bound is, the minimum, and then the value is what? Freaking 1 right here. So we're passing 1, so that's then the upper bound. Right, upper bound at that point is basically like the value, which is 5. So yeah, it's greater than the lower bound. Great. Then we go here. Okay, to the right. Doonch. Okay, this value here is less than the upper bound. Upper bound being the nose key 5 right here. And yeah, because it's invalid, then we just return false. And that is that. Hope you guys found this at least somewhat helpful. And yeah.